8.3 Linear Reciprocal Functions. I'm literally taking this out of your textbook here, so you don't have to actually write any notes. But what I want to do first is just to remind ourselves of non-permissible values. We've done non-permissible values before, but let's just remind ourselves. So it says right here, for which values of x is this? Oh, and this is, by the way, page 652 in your work text. For which values of x is the rational expression undefined? So for this one right here, I would say x cannot equal 0. Or another way that we can say it is our non-permissible values at x equals 0. When we look at the denominator of this one, x plus 4, we say that x cannot equal negative 4, because that's what will take the denominator to to 0. This one right here is a little bit trickier, because this one can be factored as 1 over x plus 3, x minus 3. So that means that x cannot equal, or I should say not equal, x cannot equal plus or minus 3. And in this one right here, x cannot equal 1 or negative 3. Now if I were writing this textbook, I would go one step further. In fact, why don't I just do it? 1 over 2x minus 5, 7x plus 9. X cannot equal what? X cannot equal, when we consider this one, 5 over 2. And x cannot equal negative 9 over 7. Because if we put this value, either one of these values, into the denominators, that will bring the denominator to 0. Now, when we're talking about reciprocal functions, values of 0 in the denominator are very, very special. And so, just to show what I mean, what I want us to do is to do this thing right here. So construct your understanding. Complete the table of values below for the graph y equals 1 over x. Describe the graph. Now what I've done is I've added these little arrows, because as the people who are watching make this video, it took me about 10 tries to do so. It's actually trickier than you might think. And what else I want us to do is I want us to fill in these values here. So if I say x is negative 5, I'm going to say y is, we're going to use the function 1 over x. So y equals 1 over negative 5. I'll zoom in just a little bit. This one right here, if x equals 2, y equals negative 1 half. If x equals negative 1, y equals negative 1. Now here's the tricky bit that gives us a little bit of pause for thought. 1 over negative 0.5. Think about it. Take out your little calculator. Negative 1 over 0.5, that's just negative 2. What about negative 1 over 0.2? That is just going to be negative 5. Negative 1 over 0.1, that's going to be negative 10. So cool, right? I think I gave a lot of you guys the spiel in grade 9 that 1 over 0 is not really undefined, it's actually infinity. So try to remember that talk from like 2 years ago, okay? Here's the crux of the thing. If I would say that x is 0 and y equals 1 over x, I'm saying that if x equals 0, I'm saying 1 over 0. We can either go, but there's nothing mathematical about that, so we're just going to erase that. Okay, no. What we're actually going to say is we're going to say it's undefined. And then we're going to move on. 1 over 0.1 is 10. 1 over 0.2 is 5. 1 over 0.5 is 2. 1 over 1 is 1. 1 over 2 is just half. And then 1 over 5. So what I want to do is I want to plot these things. So let me see how much I have here. 1, 2, 3, 4, 5, 6, 7, 9, 10, 11, 12. Okay. 1, 2, 3, 4, 5, 6, 7, 9, 10. Perfect. So I'm just going to give myself a little scale here of 1 and 1. So that means that every one of these is worth 1 and every one of these is worth 1. If we want to spend the time and go 2, 3, we can. But really just for full marks, we just need to understand the scale is 1 block this way is 1 and 1 block this way is 1. So let's plot our points. Now it's going to be a little bit difficult when we're talking about -1/5, but we'll do what we can. So we have this guy right here at x equals -5. 1, 2, 3, 4, 5. 1 over x is going to be -1/5. When we are at oh, hi, buddy. 1, 2, 3, 4, 5. When we're at -2, we're at -half. When we're at -1, when we're at -1, we're at -1. We're at -half, we're at 2. When we're at -1/5, we're at 5. When we're at -1, when we're at negative like 1/10, we're going to be at -10. So if I were to connect these lines, it would look something like this. Do 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 do. Now I don't really like that because it's getting closer and closer. Oh no. So I'm just going to erase this line here. I'm going to try it again. Okay. I'm going to start here, and I'm going to make a nice curve, getting super, super, super close to that y-axis, but not quite touching it. Then this one right here, getting super, super, super close, but never touching it. This right here is asymptotic behavior because it's getting closer and closer and closer, but will never touch that x-axis. And this one right here is asymptotic behavior because it will get closer and closer and closer, but will never, never touch that axis. I'm just going to do the same thing with this side here. Now at 0 it's undefined, so I don't make any spot right at 0. But when it's +1, it's going to be up to 10. Or 0.1 is going to be up to 10. When we're at 0.2, it's going to be 1, 2, 3, 4, 5. So more like that. Oh, where did my spot go? Then when we're at half, we're going to be at 2, +1, +1. And then we're going to be at, let's see here, when we're at x equals 2, we're going to be at half. When x equals 1, 2, 3, 4, 5, we're at a fifth. Okay. Then we're going to connect these lines, these dots again. Going to make a nice smooth curve. Do 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 psh. And then do 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 psh. And again, we have this where it's getting asymptotically close to the x-axis and asymptotically close to the y-axis, but never quite touching. This right here is the crux of this lesson, okay? The asymptotes. I want us to take down a few definitions here. So we define a reciprocal function. So the reciprocal function of f of x, where x cannot equal 0, is 1 over f of x. I just want to change this actually, where f of x cannot equal 0. There you go. Because x might be able to be 0. I'll show you what I mean. So the reciprocal function of y equals x minus 1 is y equals 1 over x minus 1, where x minus 1, which is our original f of x, our original function, cannot equal 0. So x cannot equal 1. So if we just take into consideration this one, this example right here, we would say the graph 1 over x minus 1, the graph of y equals 1 over x minus 1 has no x-intercepts because 1 over x minus 1 can never be 0. Think about it. If I would put in 1 here, 1 minus 1, ugh, we get 1 over 0. We can't get that. And what happens if I say a million? A million minus 1? No, I shouldn't do that. If I say 90, 90 minus 1 is 89. So 1 over 89. It's getting super, 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 super close to 0, but it will never actually touch 0, just like this graph right here. So we say that the x-axis is a horizontal asymptote of the graph. So just like in this case here, we have the horizontal axis as an asymptote. Now we denote asymptotes by dotted lines. And if it's on the axis, you don't have to draw over the axis, you just have to extend them with dotted lines. Trust me, you're going to love that next year in pre-calculus, or I love having that skill next year in pre-calculus, because you will be having to draw a lot of rational graphs like this. So I just want to highlight the word horizontal asymptote, because here comes the vertical asymptotes. In the graph of y equals 1 over x minus 1, the line x equals 1 is a vertical asymptote. Here's the thing, in this one, where the non-permissible value is when it's 0, so if we say x equals 0, that's this line right here. That's this vertical axis. This is our vertical asymptote. Vertical asymptotes occur when a non-permissible value is found in a rational function. So for example, the non-permissible value for y equals 1 over x, x cannot equal 1, so at x equals 1, there is a vertical asymptote. But you don't have to take my word for it here. So what I'm going to do is, no secrets, I'm going to Desmos, and I just typed in y equals 1 over x minus 1. So here's the graph. We're noticing that we have an asymptote at y equals 0, right along that x-axis. And if we look right here, we're noticing asymptotic, I'm just going to zoom out here, we're going to notice asymptotic behavior at this x equals 1. Now it gets closer and closer and closer and closer, but if I zoom in, we're noticing that it's never hitting 1. So I'm going to go down, go down, go down. It's getting so close to 1, but just as soon as I think that it's going to get to 1, we're getting closer and closer and closer and closer. if I zoom in further, you can always get closer to the 1. So what's happening is it's getting infinitesimally close to 1, but it will never actually touch 1. So this is what we call an asymptote. So just remember here, yep, that's great, thanks. So just remember here, the way that we find the vertical asymptote is finding the non-permissible values. So vertical asymptotes occur when a non-permissible value is found in a rational function.